Hello, my name is Hassan Khalil, and in this video I'm going to be walking you through how we can solve a problem using weak induction. So the problem is that we have to prove using induction that 9 to the n minus 1 is divisible by 8 for all positive integers, for all integers n greater than 0. So our statement here that 9 to the n minus 1 is divisible by 8, we have to prove this for all positive integers, and the problem is we can't simply plug in all possible positive integers into the statement and show that it's divisible by 8, so we instead have to use a technique called weak induction. Weak induction is a technique that we can use to prove that a statement is true for all positive integers. And the way we do this is through two steps. The first of these steps is proving the base case, and in this step all we do is we have to prove that the statement is true when n equals 1. Then in the second step, or the inductive step, we have to prove that if the statement is true for some n equals k, where k is greater than or equal to 1, it's also true for the following value, n equals k plus 1. But to do this, we first form an induction hypothesis, and in this induction hypothesis, all we do is we assume that the statement is true when n equals k. So we assume the statement is true for n equals k, and then we prove that the following value, n equals k plus 1, the statement is also true for that value, using the induction hypothesis in our proof. So let's apply these steps to our problem. So these are the same steps. Let's use them to prove using induction that 9 to the n minus 1 is divisible by 8 for all positive integers. So first, to prove the base case, let's simply plug in n equals 1 into the original statement. So we get 9 to the 1 minus 1. This is equal to 9 minus 1, which equals 8. And we can say that this equals 8 times 1. Now the reason I have this as the product of 8 and some integer is because according to the definition of divisibility, anytime we have 8 times some integer, we know that this number, this expression, is divisible by 8. And we're going to be using this later on in our proof. So in the second step, or the inductive step, remember we have to prove that if the statement is true for some n equals k when k is greater than or equal to 1, it's also true for the following value of n equals k plus 1. So to form the induction hypothesis, we have to assume that the statement is true when n equals k, for k is greater than or equal to 1. Then we know that since the statement is true when n equals k, that 9 to the k minus 1, we're simply plugging in k into the statement. 9 to the k minus 1 equals 8m. So remember, this is the definition of divisibility. We have 8 times some integer m, and this means that 9 to the k minus 1 is divisible by 8. We're going to use this in our proof to show that the following value of n equals k plus 1, is also true. And in our proof, the induction hypothesis is going to be used. So to start off, we simply plug in k plus 1 into the statement, so we get 9 to the k plus 1 minus 1. But in order to use our induction hypothesis, we somehow need to get this value here, this expression, 9 to the k minus 1, into our expression that we're proving n equals k plus 1. And to do this, first I'm going to take this plus 1 out of the exponent and bring it out to the front. So this is simply the definition of exponents. When 9 is being multiplied, we can take the plus 1 out. And then, to turn this negative 1 into something that we can use to factor into 9 to the power of k minus 1, let's simply transform it into negative 9 plus 8. Negative 9 plus 8, through the definition of addition, we know that this is equivalent to negative 1. But now we can factor out a 9. If we factor out a 9, we get 9 times 9 to the k minus 1 plus 8. And since we're factoring, this is simply using the distributive property of multiplication. And now if you notice, we have 9 to the k minus 1, which is our induction hypothesis, in our expression. So if we simply replace this 9 to the k minus 1 with this 8m, we get 9 times 8m plus 8. And the justification for this is simply that we use the induction hypothesis. Now finally, we simply take this 8 out as a factor, once again using that distributive property of multiplication, and we get 8 times 9m plus 1. So what do we have here? Well, we have the product of 8 and 9m plus 1. Since 9m plus 1 is an integer, and we have the product of 8 and an integer, we know that the statement for n equals k plus 1 is divisible by 8. So we know that the statement is true when n equals k plus 1. So let's recap. In the base case, we proved that the statement is true when n equals 1. Then, since it's true when n equals 1, we know that it's true for the next value, n equals 2. And so on and so forth until we know that for any value of n, the statement is true. So Using induction, we have proved that the statement is true for all positive integers. Excellent job.